G'day guys, had a SD2100 come in for repair. This one was modified by myself. We're probably going back 9 years ago, could be 10 years ago. This is an early modification with the variable gain for one of these detectors. This one actually has variable gain 3 or 4 pulse, as in the short pulses are selectable via the code in the EEPROM. It has a switch. We haven't got variable frequency in this one, but it has a switch, medium, small and deep. And what else has it got? Oh, it's got normal and bright audio as well. So that's where we are. We'll get rid of the cover. I just put that there because it said SD2100. And let's have a look at the modifications that were in this detector. I'll just zoom her in a bit. I can see what I'm doing. I'll just move that around. Like I say, this is a fairly old detector, but they're still good. There's nothing wrong with these detectors. You probably find as much big gold with one of these as any of the modern ones. The more modern the detectors are, they just tend to be better at smaller gold, and I mean fly specks. And in some cases, the older detectors, such as these, are better on bigger gold. And when I say bigger gold, I mean bigger gold. And you have more choice with coils and stuff like that. You can stick any coil on this, or any old coil, cheap, and it's going to work really well. So we'll see what I can remember about this. Now, the way we've done this, it has a couple of stages, amplifier stages. I think they're just NE5534 ICs. And what we've done here, as I think it's one of these, this is from memory, this is going back a long time. This is the dual transistor thing, whatever it's called. LM, what is it? Oh God, I can't remember. Is it bloody, yeah, anyway, those things you can't buy anymore. We haven't been able to buy them for years. But yeah, it's just a super beta transistor. The number just escapes me. What is it? What is it? I should know what it is. Come on, come on, come on. LM394 rings a bell. That's what it is. Knew it was LM something. I still want to get the numbers wrong. I've done that, trying to guess the parts, trying to remember from years ago, and you just say the wrong number. But it actually is LM394, and it's a very, very low noise device. Very low noise, but like I say, there's no amplification with it. It's only a transistor. Well, 2 transistors, and they are matched, and they are on a common substrate, which is very thermally conductive. And the reason being, you have to have your, if you're running a differential front end, you don't want one transistor drifting temperature-wise with the other, because the detector is going to make a howling noise and carry on. But anyway, I digress. From the LM394, it has goes into an op amp. Basically, one side of it's connected to the non-inverting, the other side of this LM394 is connected to inverting and non-inverting. So when there is a change on the input of this device, that op amp will swing up and down in its output. And what I've done is, from this one here, I have it uses a 3.3K interstage resistor from the output of this op amp here. You can see it, and that goes to the next op amp stage. So it's just a buffer. And what I've done is the intercoupling resistor, I just split that into 2 1.5k ohm resistors. I have one resistor on the output of the first op amp going onto the input of the variable frequency, and the variable frequency output going through the other resistor. Now, you'd think that you wouldn't need these resistors because, you know, why would there be any loading on stages? Yes, there is actually. And I experimented around with different values on these two resistors, you know, higher, lower, lower, higher, and just seeing if I can get some extra performance. And at the end of the day, I settled on a 1.5 in and a 1.5 out, which is basically the same value of the 3K. So it's giving a similar isolation on the output of this op amp from the LM394 and to the input of the next one. You don't want to cause any loading on inputs and outputs on these detectors. It just slows things down, doesn't work properly. So that actually was a good combination. What else was there? Oh, this one's had the power supply done as well. I might have to turn it around for that a little bit. In here, I got rid of that radial inductor, and I've put a shielded type of inductor on the circuit board here. You can see that. That's tucked in there. That actually does help a little bit. For the variable, or should I say for the switch frequency, you can probably see at the back there, some capacitors have been removed, and it's been reconfigured, and there's a switch put in there. On the back panel, a higher efficiency diode on the output. It's a 3 amp ultra fast. What else was there on this? Yeah, I just noticed too that the two output MOSFETs, the IRF 710s, I think they are, a little bit brown on the paintwork at the top there. That indicates that they've been delivering a fair bit of current in its output, and it's got a little bit warm. Won't hurt it. It's only the paint. It's not hurting the devices. So it's not very discolored. It's happened over a long time. So it's probably okay. If you really wanted to, you could upgrade these MOSFETs. They're damn old, and put in lower on resistance type MOSFETs, just 200 volt rated. You know, what are these? They're probably about 3 amps or something. You know, nothing wrong. Put a 10 amp one in there, a couple of 10 amps. You know, you might get a smidgen performance upgrade, but it would be nothing worth writing home about. It would just, you know, get a little bit of less loss to the coil. But anyway, that's neither here nor there. It's just been stretching things a little bit. Okay, this one on the other side, the N-channel FET, which normally lives on the other side, which it looks like this. Now, let's put it on my hand so you can see it. That's the N-channel input FET. They are little signal FETs, they call them, signal FETs. And I think diodes, or what do they call it? ZTEX or ZTEX, however you want to say it. But yeah, that was partially conductive, and that upset the P channel which it goes into. So what I've done here, I've got some better devices, and rather than trying to fiddle in here, as you can see in here, trying to stick them. If you actually have a look, I'll spin it around again now, because I've done that. All the wires will pop off, won't they? No, they won't. I'm just having a muck around. But if you can see in here where those devices were, if you can see, which I've got this switch wire here stopping me doing things, but I'll zoom in a bit. I'll zoom in if I can. All right. Okay. I need something more pointy. If you can't see, here I use this little X-Acto knife. Okay. The N-channel input FET lives there. You can see those 3 little dots of solder, and the P channel one lived here. On those 3 little dots of solder, basically, I just heated solder up from the other side and just pulled the things out. Now, both of these devices have around about 10 or 12 ohms of resistance. That's a lot of resistance to have in the front end, but they do have very, very small capacitance values. The input capacitance is around 20 or 30 picofarads or something. It's very, very small. So you're not going to get much loss in that regard, but you will have loss in the resistance. The signal trying to travel through that resistance to get to the first stage. The other thing too, which this has not got a switched damping circuit. It's all these resistors here. I think I better zoom out. But all these resistors here, it's just coil damping, and it's just straight across the coil. There's no way of switching it out, so you are going to get signal loss via the damping circuit. There's no way around that. Well, there is, but you'd have to start putting a subboard in and switching these in and out depending on receive and transmit cycles. Well, over we go, and if you can see on the board, I'll zoom in again because otherwise you're looking at fly specks. You can see that I have put in a 2SK 1334 as a replacement to the N, and I've actually had a few of these newer ZX or ZTEX devices. These are a lot lower on resistance. I think the capacitance is still around about 45, 50 picofarad on the gate. The rest of the capacitance around the devices, something like 15 or 5, or was it 10 and 3? I can't remember which one's which, but very, very low capacitance, and that's a lot more beefy of a front end. So I don't know if you can see it. You can't put any of these newer devices straight in because the center connection on these older ones is always the gate connection, and with the modern ones it usually goes gate drain source, so they're not in a line. So what I do is just move it, get the device, move it across two, so I get the gate, and then the drain is connected, and I just loop a wire around, back around to the source connection here. So you can see that little loop of wire there that goes. So it really was sort of 1 pin, 2 pin, 3 pin, and there's no pin on the far one here. I put a wire around back to the first pin because that's a configuration of how these devices are. I'm very lucky with this ZX one here, or ZTEX, diodes, whatever they want to call themselves these days. But that one there has got the center as gate. So I just stuck it on the back of the board here. It's fine. Works perfectly fine. So we got rid of a lot of resistance out the input circuit, but the big bugbear is the damping circuit across the input. Unless you run a double D coil, then you haven't got the damping circuit across the input. So with these older detectors, you probably find that you might be better off using double D coils on these rather than monos, because you're isolating the receive signal path onto the secondary coil and doesn't have damping. I haven't tried it. You'd have to try this out in the field. You can't do it in suburbia. It's impossible. Even though here I'm using this on a cancel coil, as in a figure 8 coil, and it's just so noisy. You can't really run any appreciable gain or anything like that. But at the moment, I'll just turn the audio down on this because when these fire up and into the high gain amplifier, it just wants to scream. So on it goes. I'll just turn it up a bit. Oh, there we go. There you go. She's on. I've got the gain turned down because this one has got variable gain put on. Yeah, it sounds like it wants to take a little while to stabilize. That it's hard to explain the sound, but yeah, it's got that sort of I don't know how to say. It's like a sort of a sound to it. That can indicate that the receiver is still getting some input near the flyback. It's just a characteristic noise they make. It might not be. Or maybe I've got the tone set a little bit low and I'm not used to it. But I do recall a sort of a groaning sound can be because there's something still wrong with the input stage. I'll investigate anyway. It may be because I've got it on the figure 8 coil. Figure 8 coils, the way I've done it, it does cause some interesting issues with receive, but it's the only way I can do it with these detectors here. You know, otherwise I won't be able to test them. So yeah, we'll spin this around slowly. I'm happy to loosen that off. Okay, and if you look down there, there's the figure 8 coil sitting on a detector shaft. It's not really the best. It's a bit too close to the ground, and you know there's AC wires and so forth, definitely with currents going through. But we've got this here, and you know, I've got the gain turned down, so yeah. Okay. Yeah, I think that's turned the gain full. There we go. So it's a bit noisy. You can hear it now. Now it sounds more normal with the punches of the AC leakage and so forth just coming through. You turn up the threshold and kill that a little bit, but that just um, is not proving a point. So these detectors give you an idea. Now it's very, very difficult to do any sort of a test that's meaningful with a cancel coil like that. It's not cancelling very good because I think it's actually a bit off skew. You can see it looks like it's got a few. It's not even anyway. It's got to be perfectly even. Both circles have to be the same diameter, and you know, not one looking like an egg and one being a circle. It's got to be the same, or else you have a problem. And actually, just pointing the camera at the coil has actually increased the noise, which I've heard come up as I turn the thing around. But for a target, I was going to use a battery, you know. You probably get a lot further than what I'm getting with a battery if we didn't have all that chatter and it was a equivalent size, just a pure mono coil, because you're losing half the receive and you're losing half the transmit with this coil because the energy split between the two coils and both coils are not in phase, they're in anti-phase. So that, you know, it's probably a lot worse than how it's even really going to behave in real life with a mono. So it is a big reduction in performance using a figure 8 coil. But Kalgoorlie Hot Rock, I think I actually adjusted this and did the ground balance, so it should be ground balanced. We'll just try it. Nope. So what I'll do, I'll click it into, I think that's channel 2. Let's have a look. Yes, it must be. I'm just adjusting. Getting there. I'm just doing very slow increments because I wasn't far off the mark, I don't think. I think I actually went past the mark. Just riding on the AC noise. But that is channel, what are you? Channel 2, just making sure. You know, like I say, I haven't done one of these old detectors for a while, forgetting, you know, channel 1 or 2's down the bottom, but it is channel 2. And I'll flick the switch into channel 1. Okay. Channel 1's out as well. Going the wrong way. There we go. Close enough. I think it's just riding up on the noise. So this is, we'll give it a test with a 0.1, the 0.1, see if it picks it up. So that detector's working quite good, picking up a 0.1 on the cancel with all that rat-a-tat-tat noise coming in. I'm just going to turn it down because I'm going to turn the gain down. Should have really come up with a blanking circuit for that, shouldn't I? Just to delay it, but it's what it is. Yeah. So that's the 21. I'll just disconnect it from power. Take the power out. You take the coil off. Okay, turn this around again. Here we go. Zoom it out a bit. Okay. So I've got to get this apart. I had to take the switch out for the ground balance channels. Yeah, so it's not a bad detector. It does work. It does work. And there's all the modifications that have gone into this. I just noticed the blue potentiometer. That was done a long time ago. That one. You can see. I think it's the old. I can't remember what we used to make those labels. Some sort of label maker or some description. I don't do that anymore. David looks all after all that stuff, so I don't know how he does it. I just do, like I say, I just do the design stuff and a little bit of putting the boards together and that, but you know, that's what it is. So we've got the blue pot there, it's gain, normal and bright, NB for the audio, just basically switches in, you know, like basically a capacitor that knocks off the low frequencies and takes the capacitor out of circuit to give it a bit of a brightening up of the audio. Some people like bright, snappy audio, some people don't. And the other thing we do on this as well is we, because we can access the code in the EEPROM, you can see 3 and 4. This basically, number 4 emulates the same pulse output of the SD2000. And when you put it into 3, it emulates the pulse output in the later detectors. You know, basically like a GP detector, where you'll have 3, you know, reasonably short pulses, all the same width and all the same amplitude, and after they go through, then out comes the long pulse, which is for memory, I think it could be about 240 microseconds long. Or is it 120 microseconds long? Like I say, a lot of these detectors have different pulse lengths. Now the newer ones, I think, are about 35 microseconds long, and the older ones are 60. And as long as the mathematics of the small pulses work in relation to the large pulse, the ground balance works with a funny offset in there to handle magnetite and maghemite, not just ironstone. It was one of the big bugbears when Garrett's brought detectors over here. They work beautifully in the United States, and they brought them over here and they wouldn't work. They wouldn't ground balance. And I remember Charles Garrett had to basically said, "Nah, they're pulling my leg." In stronger words than that, and he flew over to Australia. Yeah, and observed it firsthand, and yes, went back and made some modifications to the detectors so they would ground balance. But the one who had the edge on the ground balancing here for our conditions here or some other places in the world too was Minelab, because Bruce Candy actually worked out what was going on and applied for a patent and got the patent to cover the ground balance techniques, or offsets we'll call it. Should we call it offsets? Techniques? But yeah, it's a very interesting patent to read, how it all works. It's online. I think it's on Minelab's website. Yeah, Introduction to Metal Detectors, and it goes through all the different types and how they work. So hopefully it's still there. But that's the SD2100. Opening him up. Like I say, this is the whoopsie, there we go. That's the capacitor we put in switching in and out of circuit for bright or normal. And yes, there's most of it's on the variable gain. The variable gain is probably the most important. And variable frequency, yeah, it actually does help. And I'll tell you another thing too with these detectors, because we can access the, I'll show you where it all is. The code lives in that. There we go. That's an EEPROM. It's 26C256, I think, for memory, or 512. I can't remember if it's 256K or 512. Maybe it's a 512. I don't know. You can put both in there as long as the addressable lines are all the same. And yeah, that's where the basically the code is, as in if you have a look how it's done, it's basically X's, I think it's X's for off and zeros for on, and as it's clocked, they basically, gives an output of what it wants, and you get some other chips here which divide down and make your other timings. So that is how, well, not how it all works. It's basically the interesting parts of it. This board here, that's all audio. There's audio filters, and very, very interesting way it's done. It's old. The way it's done is very old. There's chips in there you cannot get anymore. And yeah, some very strange things as well. But that's this. Main thing is clean up the power supply. You can start filling it up with capacitors. Let's lift this up a bit. You can, you got to remember that the way this works, okay, ground or negative battery volts is actually set up on these detectors to be minus 5 minus battery volts. Like if it's a 6-volt battery connected here, it's actually minus volts because the positive goes to ground, and then they step the voltage up another 5 volts above ground. So they're using the battery as a negative 5 volts, and they're using the positive of the battery as a ground for both, and then they're stepping it up with the inductor, and I think it's a 4093 in here. It's clocked out of here somewhere, out of the oscillator. It goes into 4093. I think it runs at 62 kilohertz. Anyway, it generates a positive 5 volt supply for all the ICs. So that's how it works. And the reason why that is done is because the way the transmitter works, you can't, if you want to make the transmitter work nicely, you have to change these to P-channel MOSFETs. And back in the day, P-channel MOSFETs rated at 200 volts were like rocking horse teeth. You couldn't get them. So the way they've done it is this switches technically it's a negative voltage, right? And the flyback is positive. So you could change it around to switch a positive voltage, but then you'd have to change from the N channel into P channel. There's probably other ways of doing it too. You can probably use a bridge or something, and you could switch it both polarities. Lots of different combinations. But that's very, very old modifications. Very old indeed. Like when we start going to the new stuff, I haven't got any boards kicking around. Still getting made. Okay, but yeah, that's the 2100. Great for big gold. Will work on small gold. You just got to speed it up a bit for small gold and quieten it up a bit. And like I say, it might be interesting to even note these LM394 chips, which you can't get. Actually, you can get a replacement. It comes from Latvia. If you want that type of chip, it's not as low noise and doesn't have a super high beta rating as what these are. So basically, it means gain. These have a gain of about 500 to 600, and a very high cutoff frequency. I think these run to 325 megs for their 3 dB point for memory. It's very, very high. Anyway, and they're specially made so they don't drift. If you just got rid of this and you put 2 normal transistors in there, you matched them and everything, and you stuck them together, what would happen is you'd have temperature drift between the two. You won't get really good thermal coupling, and it'll be a laggy type of thermal coupling. And if you get a temperature differential between either, the detector will be going woo or woo, depending, and it depends how fast the temperature changes, is how fast that noise is going to come through. It'll drive you bonkers. I have tried it. I tried using some very, very low noise transistor stacks as a replacement for this. Now I'm getting down to about 0.3 dB noise figure type stuff, and it was impossible to match. I just breathe on it from about a meter away, and it would howl. You just could not stabilize it, and you could fill it up with all sorts of insulation and whatever, but it just wouldn't track properly. So you really need the transistor dies. The die is a little tiny transistor part, the active part of it, the bit that is big as a pinhead. You really want that on a common substrate. So, like beryllia or something like that, or some very heat conductive ceramic, so that if one heats up, the other one heats up near enough at the same time, and they can track each other, so you won't get any horrible noise. So that's this design. This device is in the 2000, 2100, And in the 2200, they went to op amps. They started running LM or NE 5534s, and the later ones have the AD797s. And yeah, and the ones I do for upgrades have better devices again. So that's that, guys. Hope you enjoyed that one. Going back into the past, delving around in this old technology. The thing is, though, right, it's still quite usable today. These will find gold, no problem. If you want a cheap detector, get yourself one of these. You can do a lot to it. I mean, if you really want to quieten it up, don't run the switch mode power supply. Remove it and use a 2-battery system. Right? You can get a lithium pack or something of that nature and just center tap it. I've done that before, and it gets rid of all the power supply noise out of the circuit, makes it much more sensitive. So a 2-battery system on these older detectors is well worth it. The only trouble is you're going to get a lot more drain out of one battery that's powering the transmitter than the battery that's just powering all the 5-volt rail for the ICs. But if you get a big enough pack and it's set up that you can run it for 8, 9, 10 hours, well, just you get a good charging system, it'll charge up and it'll all equalize out, and you're ready to go the next day. But you could do that. That's one way to do it. There's other ways of doing it. It becomes really complicated. You could always go for the stop-start power supply, but that has problems as well, I've discovered. You need a very fast oscilloscope to see what the problems are, but they are there. The better way of doing it is a complete redesign and keeping your power supply away from anything sensitive and proper board layout, proper shielding, and you can get the noise very low. I've done experiments myself with these. I've got the noise down well under 2 millivolts peak to peak. Even that, to me, is too much to have floating around on a circuit board. But this switch mode here, I think the noise, if you go and measure it around the input stage, you're sitting at somewhere around about 15 to 20 millivolts peak to peak. That's not a good thing, not near sensitive electronics. You're trying to look for, nanovolt signals. Uh, that doesn't make sense, does it? It's like a whisper listening to a band. You're not going to hear the whisper. But, it does, this quietens it up a fair bit. It does drop the radiated noise down quite a bit. The other trick you can do with these type of detectors, and we've done this in the early days, but I didn't like doing it because there is an issue. But what we used to do, we used to get steel wool, the really fine steel wool mesh, and we used to put it in a plastic bag, put it in 2 plastic bags, right, small ones, and fit it into the electronic area or between the boards and push it in there. Hopefully you don't have any pointy bits stab into the steel wool and cause a short circuit or anything, but you can actually do things like that. And the steel wool, because it's very, very resistive and very fine, any radiated emissions from the board just get shorted out by the steel wool. Doesn't have to touch anything, just has to be there. So that's one way of doing it. There's other ways of doing things as well, but it becomes expensive. You could say, "Oh, I'll paint up carbon sheet or something and put it in." Don't do that. Doesn't work. It's got to be substantial, because a lot of the problem is not just electric field, but it's magnetic field, and magnetic field's really hard to stop. You can redirect it, but with a stack of steel wool in there, it actually has an effect. So something to be wary of. Anyway, enough waffle on this one. I did have some other videos I was going to put up, but bloody audio died in the middle of it. It happened on another video I've got up there too. The audio disappeared at the end of it, so it's a bit of a problem. Yeah, anyway, that's that. Catch us.